Dear Neet aspirant, today we see that mesomeric effect as well as the resonance effect is nothing but the resonance effect more resemble to the mesomeric effect. Actually, the mesomeric effect, that is the polarity of the bond or polarity is developed in a conjugated system by the complete transfer of non-bonding electron, or there is a lone pair of electron. There is a resonance effect means there is a resonance effect. It's only for the pi bonded electrons they have creating the polarity. Okay, so there is here it's a pi bonded electrons. Bi bonded electrons they have can be polarities developed from the conjugated system. Okay, so that two kind of mesomeric as well as resonance effect more resemble to each other. That's why we can cumulative in the both two effect in this video we will see. Okay, so now simply taken as a aniline molecule. See this aniline molecule here NH2 group. Okay, so this nitrogen is possessed one pair of electron. In case of aniline nitrogen, it possesses one lone pair of electron. If this lone pair of electron is come to here, this pi electron shifted here. Okay, so it's a resonance. Another one canonical structure. Here is double bond NH2. Here is a plus, here is minus, and here is a one double bond, and here is one double bond. Now this bond is shifted here. This electron come to here. Okay, so this canonical another structure here. This double bond minus. Here double bond NH2 plus. Okay, so now this electron come to here, this pi bond is shifted here. So then another one canonical structure here, there is a negative charge, and here is a double bond NH2 plus. Okay, so anyway, the resonance is originating from that lone pair electron. See here, this resonance is originating from that lone pair of electron. Okay, so simply we already say that the polarity is developed by that complete transfer of non-bonding electron. That's nothing but the mesomeric effect. Okay, so the resonance effect, if you assume this aniline in the acid medium, it will form that anilinium ion. There is a NH2 in presence of acid medium. This is a base. Okay, this for Lewis base. This hydrogen is a Lewis acid. So between these two, we can get the anilinium ion. Okay, so this anilinium ion we can get. Now, if you consider this in this anilinium ion, whether they have mesomeric effect or resonance effect. Okay, so now see this anilinium ion here as NH3 plus. Okay, so now here this nitrogen does not containing the lone pair of electron. That's why here the resonance originating from the pi electron, or the polarity is developed by that pi electron. Okay, so this this bond shifted here, and this bond shifted here. Okay, so what will happen? It's a canonical structure here. There is a NH3 plus, there is a plus is minus, and double bond. This electron now come to here. This bond is shifted here. So actual another one canonical structure. Here is a negative sign. Here is a positive sign. Here NH3 plus and double bond. So this electron shifted here. This bond come to here. Okay, so this is become to the negative sign. Here is positive sign. NH3 plus. Here is double bond. Anyway, simply you understood the same charge at the more nearer, there is a very less stable. Okay, so that kind of resonance is not possible. If this it is possible. Actually, see here there is a NH3 plus this double bond. This bonded electron shifted in this carbon. Okay, so now what did happen? This is NH3 plus. Here is a negative sign. Here is a positive double bond. Now this electron come to here. This bond shifted here. Okay, so like that, etc. So whenever that the positive charge is more nearer negative charge, there is a stable comparatively this kind of the canonical structure. Here this positive and positive as a more nearer. That's why this stability is very less stable. Okay. So anyway, from our content, this resonance effect, the polarity is a complete transfer of a non-bonding electron. It is for that is a mesomeric effect, and the polarity is developed by complete transfer of the pi bonded electron. That is for the resonance effect. Okay. Thank you. But next actually the mesomeric effect as well as resonance effect, M effect as well as R effect. It can be classified in two types. One is a minus M effect, or there is a minus R effect, and another is a plus M effect, or there is a plus R effect. Like that, there is classified in two types. First of all, there is a minus M effect and or there is a minus R effect. We will see now. This nothing but the electrons is a transferred of a pi bond takes place from the conjugate system. Okay, the electrons takes place. The electrons takes place from the conjugated system. Just you can keep it in your mind, there is a conjugated because we will teach later for that hydrocarbon unit in the conjugated in and accumulated whatever the like that, etc. So how we can say this is a conjugated means. Okay, for example, this CH2 double bond CH, and here is NO2 N double bond O minus. Here is nitrogen as a positive sign. Okay, so now this pi electron can be shifted to here, and this bond go up. So actually it's a resonance. What we can get? Yes, CH2 plus and CH double bond N and O minus. Here is the O minus. Here is nitrogen as a positive sign. Okay, anyway, a molecule containing the equal of positive and negative sign, that is become to that neutral. Okay, so that's why this molecule is representing as there is a CH2 double bond CH NO2 like that. Okay, so now the electrons transfer aptitude is more probably for a lone pair electrons greater compared to that bond pair electrons. So these lone pair electrons, phasial electrons, that's why this lone pair electron can be more easily transferred into that chemical reaction, and compared to that bonded electron. This bonded electron, there is two types. One is for sigma bond, another is a pi bond. Here the reactivity for that pi electrons or pi bonded electrons is more reactive compared to that sigma bonded electrons. Okay, so this pi bonded electrons migration, there is a more familiar because there is a pi bond by formation of lateral overlapping or sideways overlapping. It's a weak bond compared to that sigma bond. The sigma bond has a head to head overlapping or that axial overlapping. It's a stronger bond. That's why this there's a lesser aptitude of electron transfer. Okay, so in this case, like that, the electrons gained from the conjugated system, that group are called, that is a minus I effective group, or that is a minus R effective group. Some group are examples, there is a NO2 and CN, and there is a SO3H, etc., etc. Okay, so those groups are taken from the electrons in the conjugated system. That's why there's a minus M effect, or there's a minus R effect. Another one category, there is a plus CM effect, or there is a plus R effect. Here there is a electrons or a gain from the, or electron takes place from group 2 conjugated system. The electrons takes place from group 2 conjugated system. Okay, conjugated system. Okay, so generally in the previous case, the electrons takes place from the conjugated system to group. In the plus M effect or the plus R effect, the electron takes place from the group 2 conjugated system. For example, that there is a NH2, it possessing a lone pair electron. Here is a CH, and there is a CH double bond, CH single bond, CH double bond, CH2. If we see this molecule, this lone pair electron is shifted here, this pi bond is shifted here, and this bond is shifted here. What did happen? It's a canonical structure. Yes, there is a NH2 double bond, it's a plus. Here is a CH single bond, here CH double bond, and again CH single bond, CH2, here is a minus. This polarity is developed by that the electron transferred from the group to the conjugated system. So like that, the any group is possessed, that is under the category of plus M effect or the plus R effect. There are some groups or examples. There is a for example, there's a O minus group, and there's a NH2 group, and there is a NHR group, and there is a NR twice group, and OH group, etc., etc. So anyway, the conjugated system containing group, if at least one lone pair of electrons must be presented in that group or under the category of there's a plus M effective group, or there is a plus R effective group. Okay, okay. Okay, let's see that the condition of resonance structure, resonance effect. There's a condition of, there's a resonance effect or a resonance. Okay, conditions of resonance. The first one. Now all the arrangement of atomic nuclei same. All resonating structures, all resonance structures of arrangement of atoms, atoms same. Okay, so this for the first conditions. For example, in the case of acetaldehyde. Okay, see in the case of acetaldehyde, here there is CH3, C double bond OH. So another one resonance structure, there is a CH2 double bond COH. Here is a hydrogen. Here anyway, the total number of carbon and hydrogens and oxygens, whatever that they have similar, same. Okay, the next condition, there is second category. The second category, as there is a resonating structures must have the same number of paired electrons. Resonating structures, there is a must be same number of unpaired electrons, or there is a bonded electron as well as or same number of unpaired, and there is a paired electrons. So there is a same number of unpaired as well as paired electrons. This is the second type of the conditions. Then a third one, the different resonating structures must be the same or nearly same energy. Okay, there is a third one. The energy must be same. Energy, there is a must be same. Okay, the energy must be the same. Then the fourth one, there is a atoms, the part of delocalization must be plane or nearly planar. There is a planar is must be, okay, planar of atoms in the molecule, planar atoms in that molecule. Okay, then fifth one, there is here the resonating structure, structure, if obeying octet rule, there is a stable resonating structure, obey that octet rule. Okay, this octet rule obey is must be then only there is a more stable resonance structures. Okay, the next the more resonance is directly proportional to more stable. More resonance is directly proportional of the more stable compound. Okay, the condition of resonance, there is a very, very, very important. The condition of resonance. Here, for example, see that one olefin CH3, CH double bond, CH single bond, CH double bond, CH2, and there is a CH3 like that. So generally, this pi electron cannot move to here. Okay, this pi electron cannot be moved to here because this carbon is a fulfill of a 4 sigma bond, so it cannot possess that vacant orbital. That's why this pi electron cannot move to here. But this pi electron shifted here, this pi electron shifted here. Okay, so actually it's a resonating structure of another one. There is a CH3, CH plus. Here is CH double bond. Here is a CH single bond and CH2 minus. Okay, so this is a possible resonating structure. This pi bonded rear of that carbon, if cannot be possessed as a vacant orbital, that is cannot be gain the electron from the pi bonded carbon. Okay, so this is not possible. This is a possible. Then next, suppose see the CH3 CH is double bond CH, and here is CH2 OH. Okay, so this oxygen is possessed as a two lone pair of electron. If you assume these two lone pair of electron cannot be resonating here because this carbon does not contain the vacant orbital. Does not contain the vacant orbital. That's why these two lone pair electron cannot be shifted here, and also this pi bond cannot be involved in that resonance. Okay, this cannot be involved by the resonance. Okay, so the resonance means there is a planarity must be needed. Planarity means whether the compound of carbon possessed as sp2 hybridization, that is a planar geometry is possessed. The next category, there is the same charges or nearby, same charges are more close to each other or nearly there is unstable. Same charges nearly unstable, and opposite charges nearly as a most stable. Okay, for example, see CH3 C double bond O, and here as a CH double bond CH2. If you see this molecule, this pi electron cannot be shifted here because this oxygen has a more electronegative. Electronegativity here, this oxygen is greater than carbon. That's why this is not possible. Comparatively, this is not possible. This is comparatively this resonating experiment. There is CH2 and okay. So this electron shifted here. It's a possible. Okay. So whenever that from this category, more electronegative atom must be possessed as a negative sign. Comparatively less electronegative atom. Okay. Actually, next that is application of M effect. It's an application of M and as well as R effects. Okay. Okay. So generally, the applications, first the stability of carbocation, free radical and carboanion. Okay. So in generally, the carbocation and the free radicals are electron deficient. This is the electron deficient. Okay. This carboanion are electron rich. Okay. In this video already we teached already we thought there is a stability of carbanion and free radical carbocation like that. The electron donating group is directly proportional to stability of carbocation and stability of free radical, and inversely proportional of stability of carbanion. Okay, so there is a directly proportional to for electron withdrawing group in the stability of carbanion. So this is a very important like that we told. Okay, so in the case the electron donating group that is equal for plus M effect and plus R effect, and already we studied there is a plus I effect, and the electron withdrawing group that is equal to minus M effect and minus R effect as well as minus I effect. Those are that group they have electron withdrawing nature. Okay, so depends on that we can study the stability of carbocation and carbanion. There is another examples. For example, CH2 double bond CH2 plus and CH2 plus. Okay, so these two carbocation they have primary carbocation, but in the case of this is a allyl carbocation. Actually this pi electron can be shifted here, so it will occurs the resonance stabilization CH2 plus here is CH double bond CH2. So these two is a canonical structures, but this is a cannot be stabilized by M effect, but it is stabilized by plus I effect. So in generally the M effect always greater than I effect. The role of M effect always greater than I effect because the M effect is a migration of lone pair electrons or it's a pi electrons. Here we can cumulate that both mesomeric as well as resonance effect. That's why I'm saying lone pair electron or that by electron migration, but in the case of inductive effect there's a sigma electrons can be migrated. The migration aptitude, there is a lone pair electron is greater compared to that bond pair electron. For this bond pair, pi electron is a greater migration aptitude compared to that sigma electron. For that reason the M effect always greater than I effect. So this carbocation is more stable compared to this. Next one thing, we see this CH2 double bond CH2 plus and also CH2 double bond CH2 plus. This also primary carbocation and this also primary carbocation, but here this is the most stable compared to this because this pi bonded electron cannot be stabilized here. Okay, so this is not possible. So this is a less stable. Okay, so this is a less stable compared to this. This is a more stable. Okay, this is a more stable carbocation. It's for less stable carbocation. For that reason, this is a more stabilized to that M effect. But in the case of these two, carbon has sp2 hybridization. These two is also there is a sp2 hybridization. But here that lone pair of electron cannot be, or the pi bonded electron cannot be stabilized in this electron deficient nature. Okay, okay. Then next, if we go to that another one example, there is a cyclic compound. This cyclic compound here there is a CH2 plus here is a double bond, and this compound here there is a plus charge, and another one example here is double bond is there. Okay, so next there is a here this containing here double bond, and this is a positive charge. Here is CH3. See this carbocation as a tertiary, this as a secondary, this as a primary, this tertiary, secondary, this for primary. So this already we initially teached this plus charge containing carbon, whether it is substituting depends on the number of carbon. Based on that there is a tertiary, secondary, primary like that. In this case this is a plus I effect, and here also there is a plus I effect, and this also is a plus M effect or plus R effect. For that reason, this is a more stable, and here as a plus I effect is there. Also there is a plus M effect or there is a plus R effect. Okay, so that is why this is a more stable. Here there is a only for there is a plus M effect or plus R effect. So there is a extra stability. It's a greater number of the plus I electron donating group and plus R or plus M effect. That's why there is a more stable of this compound compared to this and this. The next actually see another example. This compound it possessing the here is a positive sign, and another one here is double bond, here is a positive sign, and another one case there is a here is a positive sign, double bond, here is a double bond is a positive sign. Anyway, this is aromatic species. This is highly unstable because whenever that the positive charge, positive as well as the free radical, there is carbon containing in the aromatic compound, okay, or sp as well as sp2 hybridized carbon, that is a highly unstable. Okay, that's a highly unstable. Okay, so in other case there is a carbo anion, there is a sp as well as a sp2 hybridized carbon, there is a stable. Okay, for example, see the CH triple bond CH. Here this after of H plus elimination we can get CH triple bond C minus. Here this carbon has a sp hybridization. So this sp hybridization, it has electron negativity is greater, electron negativity sp is greater than sp2, very lesser for sp3. Okay, so for that reason the electron cloud is stabilized through the gain of electrons or attraction of electrons from the adjacent carbon. This also is a sp hybridization. But in the case of carbocation, if like that, suppose there's a triple bonded carbon, here this is does not form because this positive charge means it also is electron deficient nature, and also this rarer carbon as sp hybridization means they have electron cloud is pulled towards itself. So this already its electron cloud is very less, and also in additionally this sp hybridized carbon also its electron pulled towards itself. So that's why this is a very highly unstable. Whenever that sp and sp2 hybridized carbon, it cannot possess as a free radical as well as the positive sign. Okay, if you like this video, you can subscribe and share your friends. Okay, thank you to everyone. We will teach next video in the hyperconjugation. Okay, thank you to all.